All right, guys. I think we are ready now. Okay, so we're going to talk about just sequences in general today. And we're actually not going to do any real calculus as far as like derivatives or integrals today with this stuff. Just want to get this down because what we're going to be doing in the next few days is going to relate directly to the idea of what a sequence is and how they work and all of that. So we're going to kind of lay down different types of sequences that you'll see and then different ways that we can analyze those. And the two that we're going to be looking at the most, because they're kind of the most common, are arithmetic and geometric sequences. And throughout your mathematical career up to this point, you may have touched on this a little bit. Like in Algebra 2 now, we've made this part of the curriculum, but I'm not sure that when you guys went through that class, this was necessarily something that was high up on the list. It was kind of one of those things that, if there's time, we'll talk about it. If not, then not a big deal. So I'm going to just kind of lay it all down here, just in case. So an arithmetic sequence, what does the word arithmetic sound like? Or if you were to read that word up there, how would you probably read it instead? Arithmetic, okay. And what is arithmetic? It's a certain kind of math. With numbers. Yeah, it's actually the non-algebra kind of math. So arithmetic usually refers to like addition, subtraction, multiplication, division, just doing like simple arithmetic. But actually, more specifically, arithmetic refers to addition and subtraction. So an arithmetic sequence, it's a sequence of numbers where the pattern in the sequence is you're adding or subtracting something each time to get from one to the next. Okay? So it's an addition, subtraction from one term to the next, and this is referred to as the common difference. So, give you an example here of an arithmetic sequence. So if we use these little curly braces to show what's in the sequence and what's not. So let's say our sequence does one of these. Starts at 2, so it's 2, 5, 8, 11, etc. So what is the common difference in that sequence? 3. Okay, because that's what I'm adding or subtracting to get from one term to the next as I go through it. Okay. Okay. Now we got two different ways that we could write a formula for this sequence. Okay. There's what's called a recursive formula, which is actually, I think, the easier. And there's an explicit. Okay. So let's talk about recursive first of all. So a recursive formula, basically the only two things you need to know to write a recursive formula is what number does it start on and what's the common difference. Okay? We've got both those two pieces of information staring us in the face right now. We've got our first term is a 2, common difference is 3. Okay? So here's how you write it. And again, this is mostly just getting this notation stuff down. So we'd say a sub 1 equals 2. Okay? So we use the letter A to denote each term in the sequence. And the little subscript next to the A is which one in the sequence it is. Okay? So this is a sub 1. This is a sub 2. This is a sub 3. A sub 4, etc. Okay? So a sub 1 is 2. Equals 2. Yeah. They usually use an A for the first first sequence, and then they'll use B's for the second sequence. But we're really going to stick with just A's, what we're doing. We're not going to have multiple sequences working at the same time. But you're right. Okay, so that's the first term. And then the recursive part of it, something that's recursive is recurring, it keeps going. A recursive formula shows you how you use the term before it to get to the next one. So in addition to that, you would also say a sub n plus 1 equals a sub n plus 3. Take a second. See if that makes sense to you. Okay? Instead of a number, I have n plus 1, and then I have n. What is this saying right here, this second line that I just made down there? Yeah, to get to the next one, okay, assume that this one right here, this a sub n, is wherever I'm at. It could be anywhere in the sequence, right? It's n. I don't know which one it is. It could be any of them. But to get to the next one, a sub n plus 1, see how this is going to be one position beyond this one? Okay? To get to this new one, I have to take the old one, whatever it is, and add 3. Does that make sense? Okay, so it's just the notation, really, like I said, that you have to kind of get around here. So wherever I'm at, plus 3 gives me the next one. That's a recursive formula. It uses a previous term to show you how to get to the next one. Okay? And with these, usually we have like a big kind of curly, whoops, I drew that wrong. Kind of a big curly brace here to kind of pull this all together because it's all one formula, really. All that together. So the first term, because you got to know where to start. The recursive formula tells you how to get to the next one, but we need to know where we're starting in the process as well. And so that'll work. So you guys, when you've been working with equations in the past, functions, you're not used to really thinking of things this way. Usually in the past it's, I have a number for x, I want to plug it into the formula and get a result. Okay, it's the whole function idea where there's an input and there's an output. And we can think of these things as functions as well. Okay, so I'm going to take this and I'm going to just rewrite it a different way. Because we can write this formula explicitly, not recursively, using this whole function idea that you guys are used to. So my sequence goes 2, 5, 8, 11, etc. The n of each of these, this would be 1, 2, 3, 4, right? A sub 1 is 2, a sub 2 is 5, a sub 3 is 8, a sub 4 is 11. So think of it like x and y. Okay, here's what we need to try and do. We need to come up with an equation that if I plug in the n, I get the a sub n as a result. All right, and I don't want to tell you guys this process. I want you to think about it. See if you can figure out how you could make an equation that would make that work. So if you want to, talk amongst yourselves, work with the person next to you, but spend a few minutes. See if you can kind of just play around a little bit. See if you can come up with an equation that would work for that. All right, I'll let you do that. It's not going to be anything crazy, I promise. Just don't don't overthink it. If you got an idea, write it down. No? It's too amazing to write down. Does anybody have an idea, something they think works? Bailey, would you like to share what you have? I'm going to make you do it anyway. So you take this times 2. It gives you 4. Or that gives you 2, I'm sorry. Okay. So you multiply by 2 to get 2. Mm-hmm. And then you add the n above it, which is 0, and you get 2. So you're saying 2n plus n. Plus n minus 1. Like that? Okay, so 2 times 2 is 4, plus 1 is 5. 3 times 2 is 6, plus 2 is 8. 4 times 2 is 8, plus 3 is 11. So what if we simplified this up a little bit? We'd have 3n minus 1. Well, let's keep trying that out. So if we had, let's say a 5, what should be, let's use the equation here and let's see if this works. So I put a 5 into here. 3 times 5 is 15, minus 1, 14. Does that fit the pattern? Yeah. So if I did a 6, 3 times 6 is 18, minus 1, 17. It looks like we got something that works. So this would be our explicit formula. You're right. So actually you would write it this way. So a sub n equals 3n minus 1. Okay, now take a look at that equation. What kind of an equation is that? Like if I were to graph it, what would it look like? It's a line, right? Okay, what's the slope of that line? 3. Where have we seen a 3 before? It's the common difference. Okay, so there's a little relationship going on right there. Okay. So there's a little bit of a shortcut here. Okay, the fact that that slope is the common difference. You can do this as, let's see. So, okay, I guess think of it this way. This equation would be 3 times n minus a third, right? And so if we were to take... Oh, nope, sorry, did it wrong. My bad. It's already right there. Okay. This number right here we already said was the common difference. And this negative 1 actually has a meaning to it as well. Take a look at our pattern. Okay. If I were to go back 1, okay, so instead of n being 1, n is now 0. What's going to be the a sub n if n is 0? Negative 1, right? So this is the common difference. This is the a sub n when n is equal to 0. I didn't need to factor. I thought I did, but I forgot. You don't. Which should make some sense, right? If n is 0, you get this. So if you can take your pattern and take it back far enough to make n 0, then you can see what you got. Okay? And so that's a real quick way to write an explicit formula for something that's arithmetic, okay, where you're adding or subtracting the same thing each time. So let's see if we can just jump right to the explicit formula for another one. So let's write the explicit formula for the sequence. -3, -5, -7, etc. So what is that common difference for this one? It's not supposed to be a challenging question. What's the common difference? -2, right? It's going down by 2. Okay. And what does a sub n equal when n is 0? If this is 1, 2, 3, etc., what would be the one before it? -1. Okay. So the common difference is -2, and a sub n is -1 when n is 0. So then my explicit formula would be a sub n equals -2n minus 1. Okay. Again, it's just a linear function. Slope of -2, because that's how much it's changing, right? And -1 would be its initial spot when n is 0. So, yeah. That works. Okay. Recursive formula for this one could be done the same way as before. A sub 1 is -3. A sub n plus 1 equals a sub n minus 2, though, this time. Okay. So, that's pretty much all I want to talk about for arithmetic. All right. Being able to come up with the two types of formulas, recognizing a common difference, all that kind of stuff. Okay. So now we can get into geometric sequences. Now the name of this one, geometric, comes from, there is a connection to geometry of this one, and it involves triangles with altitudes drawn in them and all that, and if you had me for geometry, we actually talked about that a little bit. I don't want to get into that too much because it kind of gets away from our point of what we're doing today a little bit, but just know that the name is not just arbitrary. It does have a meaning in geometry. However, a geometric sequence is different from an arithmetic sequence in that instead of doing addition or subtraction each time to get from term to term, you're doing multiplication or division. It's really the only difference. And these, it's not called a common difference anymore, because for multiplying and dividing, it's called a common ratio. So whatever that number is that you're multiplying or dividing to get from each term to the next, to the next, to the next, is going to be called your common ratio. So, give you an example of one of these guys. See if we can do the same process as we did before. Can we come up with recursive and explicit formulas for these? All right, so let's say we got that. 4, 12, 36, etc., etc., etc. So, what is the common ratio for this one then? 3, right? Multiplying by 3 each time. Okay, so let's see if we can come up with that recursive formula again then. So the first thing that I need to write down again is, where am I starting from? Okay, so a sub 1 equals what this time? Mm-hmm. And then a sub n plus 1. What am I going to do to get to the next term? Multiply by 3. So this little formula will show that then. So a sub n plus 1 equals 3 times a sub n. And that's it. That would be your recursive formula for this one then. Okay. Challenge again is in the explicit though. So there is a way to do this by hand as well. So again, think about like a function. So if we had 1, 2, 3 for n, a sub n is 4, 12, 36. Chew on that one for a few minutes. See if you can come up with what kind of formula. Last time it was linear for arithmetic. So what do you suppose would work for this kind? Give it a try. Just play around with it a little bit. See if we can get somebody to come up with it. If you're struggling, I'll give you a little section, but see what you got. So any ideas on this one? Are we stuck? Is that fair to say? Okay. So, what are you doing each time to get from each term one to the next? You're multiplying, right? What kind of a function is repeated multiplication? How do you write something that's been multiplied again and again and again? Exponential. It's some kind of exponential type function. Okay? So, you're multiplying by 3 each time. Okay? In an exponential function, where would that show up? The number that you're multiplying repeatedly. So if I had like f of x equals a times b to the x, that's exponential, right? Where does that number go that's getting multiplied again and again and again? Is it the a or the b? It's the b, right? So in my equation here, for my explicit, all right, it's going to be, so a sub n equals something, I don't know what it is yet, times 3 to the n. what number should go in the front? What's that A? Where does that come from? It would be when n is 0 again, right? It's that initial term. So what is my A then? If n were 0, what would be the A sub n? 4/3. You'd have to divide by 3, right, to go backwards. So this would be 4/3. And that should work. So try it once. If you plug in a 1, 4/3 times 3 to the first power. 4/3 times 3. 4, right? If you plug in a 2, 4/3 times 3 squared would be 4/3 times 9. 4/3 times 9 is 12. And it works. Okay? Now, if you don't like this, if you don't want to try and think about moving this thing backwards one, there's another way that you could write this, and it's totally legit still. I could just do it like that instead. And so instead of having to move this 4 back one term, I could just use that. But then instead of raising it to the n, I have to raise it to the n minus 1, because I want to be 1 removed from where I was on the last one. And it still technically works. I mean, you can try it. If you put in a 1, 1 minus 1 is 0, right? So now 3 to the 0 is 1. 4 times 1 is just 4, so that works. You put in a 2. 2 minus 1 is just 3 to the first power. 4 times 3 to the first power, that's 12. So that still works. Okay, so it's kind of an alternate way of doing that. If you'd rather change the n into an n minus 1, and then you can stick with just the A is whatever the first term you saw in the sequence. You don't have to work it back. Okay? So let's try this once. All right, I'll give you another geometric sequence, and then see if you can write it explicitly. All right, so take a second. I'll let you try it on your own real quick. You got 6, 3, 1.5, etc. All right, how do we do? One of those two things? Good? Either 12 times 1/2 to the n or 6 times 1/2 to the n minus 1. Do not care. Nope. As long as it works, that's fine. Okay. All right. So you'll be looking at arithmetic, geometric, and then they're also going to be giving you guys some equations of some sequences that are maybe not arithmetic or geometric, that look a little bit different. So if you were presented with something like a sub n equals n times n minus 1 squared or something like that, it's still a sequence, right? It's still an explicit formula for some sequence, right? And we could construct that sequence if we wanted to, all right? And we could analyze that sequence if we wanted to and kind of see what's going on. This thing is not going to be arithmetic or geometric, okay? It's not going to follow a discernible pattern that you can see. You're not just adding or multiplying by something. There's something going on, but it's not necessarily one of those. So with these, all they're going to ask you to do probably is just, can you give me like the 10th term in the sequence? Or can you tell me, is this sequence converging or diverging, which we're going to get into a lot more in a little bit. But let's just start with something like, what is, we'll say a sub 5. Okay? And that question is actually pretty simple. It would just be plug a 5 in, and what do you get? If you have an explicit formula for something, that's pretty easy. So a sub 5 would be 5 times 5 minus 1 squared, which would be, what, 5 times 4? No, 5 times 4 squared. So that would be 5 times 16. So that would be 50, 80, right? So the 5th term in that sequence that's defined by this explicit formula would be 80. Okay? They could also give it to you recursively. Okay? Maybe you've got some kind of funny-looking recursive one where it's something like a sub 1 equals 3, a sub n plus 1 equals 2a sub n minus 5, and they could even throw in like an n like that. Okay, so it's got, not only is it using a previous term, but it's also using whatever n you're at. So for this one, what if they said, what is, we'll keep this one a little simpler, what is a sub 3? Okay, well, the downside to a recursive formula is that you have to go one term at a time to get there, right? Because a recursive formula just tells you, what do you do with the previous term to get to the next one? Okay, so you can't jump right to the 5th one like we did in the explicit one up there, because we just knew what n was and plug it in. This one, we gotta go one step at a time. Okay, so a sub 1 is 3. I gotta get a sub 2 before I can get a sub 3 now. Okay, so a sub 2, if I follow my formula here, would be 2 times the previous term, which is 3, minus 5 times n. Well, n is 2 right now. Or actually, the n would be, it would be 1, right? Because I used a 1. This is a sub 1. This is for the next one. So this would be 5 times a 1. So then I've got 2 times 3 is 6. 6 minus 5 is 1. So a sub 2 is 1. So now a sub 3, 2 times the previous term, minus 5 times the n is now a 2. So that would be 2 minus 10. So negative 8 would be that term. Okay? So whether it's explicit or recursive, you can use the formula to find terms. Just the explicit tends to be a little bit more useful because you could jump to, like the 100th term or whatever and got it. Whereas if you were asked for the 100th term in a recursive, you'd have to sit there and go through the first 99 before you could get to it. But I mean, it's still technically doable, but it's just a little bit less useful. So these are easier to come up with. It's easier to write a recursive formula for something, but it's much more cumbersome to use if you actually want to go find a term in a sequence that's a little bit more further down the line. So they're going to ask you to do that. But the biggie, that we're going to be focusing on here is converging versus diverging. Okay, so let's talk a little vocab here for a second. What does the word converge mean? Coming together. Yeah. So if a sequence converges, that means that it is coming together or it is approaching some number. Okay? So give you an example of a sequence that converges. (24, 12, 6, 3). What kind of sequence is this? It's geometric. What's the common ratio? Careful. If it were 2, it would be getting bigger. So what is it actually? It's a half, right? So it's a geometric sequence. The common ratio is a half. Okay? If I continue this pattern, this is going to get closer and closer and closer to something. To what? To 0, right? If you take your calculator once, you can do this really fast. If you just want to see what's going on. All right, I start with a 24. I know I'm dividing by 2 each time, so divide by 2, 12. And if you keep hitting enter, it's going to keep dividing by 2, right? Nope, got to do it again. Hold on. Divide by 2. There we go. Okay, so now we can continue to divide by 2. And all of these numbers are getting smaller and smaller and smaller, but they're all approaching 0, right? I'm never going to get below 0 if I keep dividing by 2, right? So this is converging to 0. It's got a limit to it, right? So for this particular one, we could say it converges to 0 as n approaches infinity. And remember, n was just the numbered term you were at, okay? So as we let n go to infinity, the sequence itself is getting closer and closer and closer to 0. Okay. Not all sequences are going to do this, though, right? They're not all going to converge. If it doesn't approach some number, then we say it diverges, okay? Goes away from, okay? So if I had one like this, let's say, (5, 7, 9, 11, 13). What's going to happen with this one as I continue to go if I let n go to infinity? What's going to happen to that sequence? It's going to diverge. It's just going to keep getting bigger, right? Going to keep adding 2 to it every time. So there's no limit to it. It's going to just keep getting larger. So this sequence, we would say, diverges as n approaches infinity. Okay, so basically what we're talking about here, guys, is limits. We've talked about this before, okay? So something that converges we would say that the limit as n approaches infinity of a sub n, so this would be the explicit formula, exists. And they diverge does not exist. Okay, But I guess more specifically, you'd say that this exists and is not positive or negative infinity, because we want it to converge to a number, not go to infinity, right? So we'd have to say the limit exists, but also it's not going to go to positive or negative infinity. And this one does not exist, or it is positive or negative infinity. We saw an example of that up here, okay? The first one converged, okay? It went to some number, 0, okay? That is not positive or negative infinity. The second one diverged because the limit did exist, but the answer to that limit would be infinity. So it fell into this category over here, okay? So it's going to be one of those two things. It can't be either or it can't be anything but those two, okay? Now, if you think about our arithmetic and our geometric, arithmetic sequences fall into one of these two categories all the time. Think about the nature of an arithmetic sequence. What has to be true about every single arithmetic sequence on the planet? Converge or diverge? Has to diverge. It can't approach a single number because you're always adding or subtracting something. So it's always going to skip over whatever number it might be approaching. It's just going to keep getting bigger or keep getting smaller, and it's never going to slow down and approach a number at all. So for arithmetic, they will always diverge. They will always either be positive infinity or negative infinity as n goes to infinity. Now, geometric, it depends. Okay? If that common ratio is something bigger than 1, think about exponential functions here again, okay? That common ratio would be the base of the exponential. If that's bigger than 1, what happens to exponentials? It becomes exponential growth, right? Which means heads off to infinity. Doesn't slow down. So if the ratio is greater than 1, it diverges. If the ratio is less than 1, actually less than or equal to 1, then it converges. And we found that with this one up here, right? This very first example we did here. This was a geometric. And what was the ratio? 1/2. So it fell into that second category, right? The ratio is less than or equal to 1. So it converged. And that one happened to converge to 0. So it works, okay? And so you're going to be asked to do a little bit of work with some explicit formulas for these things, okay? So let's try that just a little bit, okay? So let's say we've got a sub n equals 1 over 2n. And so my question is then, does this sequence defined by 1 over 2n, does it converge or diverge? And if it does converge, what number does it converge to? Okay. Now it's not arithmetic, it's not geometric. Okay, the way this formula is made, we can tell that. It doesn't look like a linear equation, so it's not arithmetic. It doesn't look like an exponential, so it's not geometric. So we still have to kind of think about what's going to happen. All right. Now you might be able to start just laying down some terms for this thing, which would be probably where I would start, is just figuring out, okay, if n is 1, 2, 3, 4, what's happening, and can I get a sense of, is it going to approach something or not? But basically, though, you're doing this. The limit as n goes to infinity of 1 over 2n. So think about that just from that perspective. If n gets infinitely large, what's going to happen to that fraction? The fraction is going to get smaller, right? And it's going to get closer and closer and closer to what? 0, right? So the limit as n goes to infinity of 1 over 2n equals 0. So the sequence defined by this converges to 0. Okay? Most of these you can just kind of do in your head like that. Just think about what's going to happen if I let n get really large. Let's try another one real quick. Let's do... say our formula was 1 over n plus 2. So the limit as n goes to infinity of 1 over n plus 2. Okay? So this one, you can think about it in two parts then. So what's going to happen to the 1 over n? What's going to happen to the 2? So as n gets very large, what's going to happen to 1 over n? Smaller again, going to go to what? 0. Plus 2. What's this equal to then? 2, right? The first part goes to 0. 2 is going to stay 2, right? There's nothing going on there. So this is equal to 2. So this one happens to converge to 2. Okay. What about that? N squared plus 1 over n. You guys remember when we talked about horizontal asymptotes? We had to compare the numerator with the denominator about which one's growing more quickly, and that helped us determine if it was going to have a horizontal asymptote or not. You're doing the same thing with this stuff, essentially. As n goes to infinity, as n gets really large, okay, when we were doing horizontal asymptotes before, it was as x gets very, very large, what's happening to the function? Same basic thing. So the numerator has a higher degree than the denominator. What does that tell you? There's no asymptote. So what does that tell you in terms of the converging versus diverging story then? It diverges, right? If it had some kind of horizontal asymptote, it would level off to that, right? Which means it would converge, right? It would approach that number, it would converge. If it doesn't, then it diverges, right? So this one, the limit as n goes to infinity of n squared plus 1 over n, that equals infinity, so this one diverges. All right, I want to do one more of these with you, and then I think I'm going to be good. So I want to introduce something to you that maybe you haven't seen before. Anybody know what that little exclamation point is? If you're in statistics, you should know, right? You haven't seen the exclamation point yet? Factorial? Yeah. It's a factorial. A factorial is this. Well, eventually you guys will see it. Anyway, so 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Basically, it means you multiply every integer from that number down to 1. Not including 0, because then the answer would be 0 every single time, right? Just down to 1. Okay? So, n over n factorial. So this n factorial will be wherever I'm at in my sequence, that number for n, I have to multiply that by every single number, every integer up to that underneath it down to 1. Okay? So just consider that for a second. So if I have n over n factorial, what's going to be larger, the numerator or the denominator? The denominator. So what is going to happen if I try to calculate the limit as n goes to infinity of n over n factorial? If the denominator is larger than the numerator. Converges to 0. Yeah, exactly. So they're going to throw a few of those at you. Okay, those little factorials. Just know this, they're super huge. Okay, when you start multiplying every number up to that number underneath it, they get really big really fast. So yeah, that converges to 0. But okay, I think that's probably good enough for you guys to get going on this stuff. So I'm going to stop my recording. Got about 15 minutes.